annual conference. This is actually the first live event since 2020. So attendance is going to be a little bit hard to foresee. But welcome to attend our afternoon session.
Thank you, Dr. Thomas Coughlin. Our next speaker coming up is Dr. Paul Rousseau. Before that, we take a moment to thank our sponsors. And let me introduce the speaker, Dr. Paul Rousseau. He's the Senior Director of TSMC. His topic today is powering the digital revolution. Excuse me. Dr. Paul Rousseau received a Ph.D. and Master of Science degree from Stanford University in applied physics. He was at Hewlett-Packard Labs prior to 1999. And he's currently Senior Director heading TSMC's Field Technical Solutions divisions. Let's welcome him.
So, okay, 你好，你好，我说中文不好。So, thanks for letting me continue in English. I'm going to talk about how TSMC powers the digital revolution, and it's really nice to be back in front of a live audience after so many years. So it's good to see some faces. And I'm going to start with an analogy, right? So I believe Moore's Law was one of humankind's great adventures, right? It was first published in 1965, but if you look at the first data point on there, it's 1959. So we've been going on this thing for 63 years. And I want to create a parallel to another one of humankind's great adventures, the Transcontinental Railroad. It was first proposed in 1845. And the idea was to connect Omaha, Nebraska to the West Coast. Actually, in this case, Sacramento. It's not quite the West Coast, but close enough. And there's a lot of analogies in how we went down Moore's Law to how the Transcontinental Railroad was built. Both of them required a lot of effort, a lot of time, and a lot of innovation. So with that, let me show you our itinerary. First, I'll do a brief overview down history lane. Then I'll focus a little bit on our advanced logic. Talk about our More Than More, which is our specialty technology, which ties all the logic to the real world. Then I'll jump in a little bit into more of more, which is putting packages together, right? Putting multiple chips together in a package to create really powerful systems. Finally, I'll talk about our Grand Alliance before summarizing. So, TSMC had some humble beginnings. We started in 1987. And this is a picture of our Fab 2. Some of you may have visited it. It used to be our corporate headquarters. It's still there, and it's still manufacturing 6-inch wafers. But today, they're gallium nitride wafers, which is a really cool technology, right? This enables you to make chargers that are either much smaller or much faster. So all those bulky wires that you're carrying around these days, those are going to get a lot smaller in the future. And that's an innovation coming from gallium nitride on 6-inch wafers. This is about maybe a decade and a half into our existence. This was a TSMC roadmap at the time. And there's two things I want you to notice on this. First is our logo. Our logo has changed. And let me show you the new logo just so you have a comparison. We made the wafer a little bit rounder, but you can also see the defect density went down. So a lot of effort on defect density reduction. The other thing I want you to notice is how the voltages match the node size, right? So if you look at 0.35, it's 3.3 volts. Quarter micron, 2.5 volts. 0.18, 1.8 volts. So we were in the era of Dennard scaling. And if Morse had a law, which was, I would say, more of an observation or a vision, Dennard had a recipe, right? And if you followed this recipe with the scaling factors, you could take a technology and scale it continuously by scaling the voltages, and you would get a faster technology, a lower power technology with more density. And that worked really well for a long time. And in those days, I would say TSMC was a little bit like the little engine that could. I don't know how many of you are familiar with that book, but we were definitely not the biggest player out there, but we just felt we could do a lot, and we worked really hard. And even though, sorry, okay, I'm locked up here for a sec. Let's go manual. Okay, manual isn't working either. So technology, oh, the other clicker is working now. I'll switch it. So in those days, even though it seemed hard, in retrospect, when we look back, we were on the easy part of Moore's Law, right? We were laying the track in the planes, and things were relatively straightforward. We were following the rules. But pretty soon, I'm just going to use both. Pretty soon, Moore's Law Dennard scaling literally ran out of steam. We just couldn't scale the voltage anymore. And so let me show you a roadmap around 2006. And again, there's two things I want you to see on this roadmap. First of all, you'll notice we have three different tracks of technology: a low power, a general purpose, and a high speed. The low power actually stood for low standby power. And all of this was limited by the gate oxide leakage and gate oxide scaling. And because of that physical constraint, we had to have those three different offerings to optimize for different applications. So basically, the technology and the physics drove the way the roadmap was done. The other thing you might notice is, and I don't show the voltages here, but when you go from 0.13 all the way down to 40, the variation in the voltages was very minute. We went from about 1.2 volt to 0.9 volts. So Dennard scaling was gone. We had to introduce some new things. So the first thing that was introduced was strain. And this is a famous example of a PMOS silicon germanium source strain, compressive strain, which brought the PMOS performance pretty close to the NMOS performance. This was compressive strain. The other example you could use would be tensile strain. And during this talk, I'm going to give you three examples of how you get a rail car up a steep hill. It's difficult because you're limited by the friction of metal wheels on a metal rail, and actually the real limiting factor is when the whole thing is wet. So there's different innovations people came up with to do this. The first one is very local. All of you should recognize the San Francisco cable car. And the way these get up a steep hill is by getting pulled by a cable, tensile strain in this case, up the hill. And you can see on the right the engine room that operates all of this. But strain got us some performance. We also had some lithography limitations. And with the failure of 157 lithography, we were left with little choices. Whoop. Okay, now neither of one works. Oh, here we go. So our very own Bern Lin proposed, and we drove through immersion lithography. And the idea there was to put a layer of water between the lens and the wafer, thereby getting the added resolution of the refractive index of the water. Now, it's not a trivial problem because these wafer stages are moving pretty quickly. You're bringing water in, you're taking it out, and you could have bubbles, you could have heat, and you could have the reaction of the water with the photoresist. But we got all of this to work in volume production. The next challenge was to take care of that gate oxide scaling I mentioned. And that was the introduction of high-K metal gate. We took care of the polydepletion effect and the gate oxide in one fell swoop. The big question facing the industry was it gate first or gate last? Was it the caboose or the engine? I would surmise that in the end, the caboose won, and gate last was a great success, although both technologies actually worked. Still, we're still facing some end of tracks. Planar was running out of steam in terms of enhancements, right? After high-K metal gate and strain, there was a limited number of knobs that we had. Lithography, we had gotten 1.5 generations out of immersion, but again, we were running out of steam. One way to solve the lithography problem was just to go with double patterning. 2 trains are always better than 1. For planar devices, we had to go vertical, make the trains go in the vertical directions. FinFET, that gave us much better gate control, steeper subthreshold slope. We got better I-off, better ion. And so we came to a more recent roadmap. And here you'll see the roadmap has distinctively changed in terms of style. What we typically do with our high-end technology is we lead with the technology that we try to bring in quickly with good ROI, good value. And then at a later stage, we optimize that technology further to offer our mainstream technology. And I'll talk more about that in terms of our derivative technologies that we offer. So if you look at that, N7 was a massive success. It was our 2nd generation FinFET, 4.7 million wafers shipped. That's a lot of devices out there. That's powering a lot of what the world you live in today, whether it's phone, computers, data centers. I mean, if we took all of those 7 nanometer chips out of existence right now, the world would grind to a halt. Very fast defect density reduction, fast ramp. And one of the things that we do very well is what I call the big die advantage. So first of all, you'll notice with the chart on the left, our defect density is better for large dies. That's actually because the yield model isn't completely mathematically correct. So it shouldn't be that way, but it turns out that's the way it is. But also, if you look at a good defect density, for a small die, it doesn't make that big of a difference in yield, right? If I have 70% yield on a small die, I've only got 30% upside. It gives you better control, better reliability, better DPPM. But on a large die, if I have, let's say, 5% yield, improving that defect density has a tremendous impact. I've got a long ways to go. I could actually multiply that yield by 20x before I get to 100%. And so really being able to drive low defect density is what enables us to deliver large dies to our customers. Again, things just don't get any easier. And sometimes you just have to believe in a little bit of magic. So for those of you who don't recognize this photo, this is actually the famous Hogwarts Express at platform 9 3/4. Maybe you have to have kids to know what that means. So let me ask you a question. How many of you in the audience thought that EUV was going to work? And before you answer the question, let me give you just a little bit of background, okay? For an EUV system to work, you drop a tin droplet. You first hit it with a laser pulse to shape it. Then you blast it with another laser pulse to collect the EUV. All of this has to happen in ultra-high vacuum because EUV gets absorbed by pretty much anything. And you have to make sure that all that tin you blasted doesn't end up everywhere on your collector as well. You do this about 50,000 times per second. You then take that collected EUV, you put it again in a high vacuum chamber. You bounce it off a bunch of mirrors. Every time you go off, you can't go through projection optics, right? Anytime you go through glass or something, it gets absorbed. So you can only reflect it. Every time it, whoops. Sorry, did I hit it? Okay, I'm one slide too quick, but I don't seem to be able to go back. Oh, there, thank you. Every time you bounce off a mirror, you lose 30% of your energy. So you can do the math with the mirrors here. Very quickly, you lose a whole lot of power. You then have to reflect off of a mask because you can't, before you would project through a mask. Now you're reflecting across a mask, coming back out. You may or may not have a pellicle solution for this thing. And then finally, you get on your wafer stage. So now that I gave you that background, how many of you had doubts whether EUV was ever going to work? Put up your hand. Wow, you're an optimistic bunch. Okay, I had doubts, especially after 157 failed. The good news is there was some bumps in the road, and we did put a lot of work into this. N7 Plus was our first EUV technology. And you can see there was a bit of a learning curve there. There's a little bit of a blip in that blue line with our defect density. But very quickly, we brought our defect density down to where it has been historically. And today, I'm happy to report that EUV is alive and well. The chart on the left shows you our installed base. We have more than 50% of the worldwide installed base of EUV tools. And believe me, these tools are very complicated and they're not cheap. On the right, you can see kind of the wafer volume that we've increased on there, 40-fold in 4 years. All of our N5 technology is a proof of the fact that EUV is alive and well. So that leads into our N5 technologies. We're no longer in the plains here. The obstacles are getting much tougher. So with the proof of N7+, we're able to adopt EUV for N5, full EUV. We adopt strain channel for the transistor, enhancing the performance. We adopted architectural features to the standard cell logics to enhance the shrinkage factor, as well as optimizing the back end. And if you looked at an optimized solution, you can see here we're getting about a 1.8x logic density shrink from the N7 to the N5. To Thomas's previous point about SRAM scaling, it has slowed down. I wouldn't say it's stopped, but the SRAM scaling from N7 to N5 is definitely slower than this 1.8. And you can also see here, we've shipped over 1 million wafers on N5. Again, that's a lot of devices out there. Very strong proof of concept. Okay, I want to shift gears now, and I'm leaving trains and going to space shuttles, right? No, wrong. This is all about trains. If you look at the boosters on the side of the space shuttle, it turns out the shape of those was determined by how they were transported from Utah to Florida, which was by train. So the width and the length had some unfortunate consequences, as you know, right? Because as they put these things together, sometimes those joints would fail, and that created problems. But the width was also set by how wide you could put something on a railroad car. And there was a story going around the internet a few years back about how that was related to the width of 2 horses. And the story went a little bit like this. Romans were very good at building roads. And as people built chariots to go on these roads, they typically would build them the width of 2 horses. That would create ruts in the roads, and if you didn't have the right axle size, basically you would break your wheel. So it created some kind of standard for how wide the wheels would have to be on your chariot for you to use the road in a functional way. And when the railroad cars came along, the people who were building the chariots started building the rail cars. And so we ended up with the same standard that the width of a railroad car, the wheels, is pretty much the width of 2 horses. Now, why is this important? It's just an interesting story of how standards matter. If you were to look at this train as an engineer, you might say, if I was designing this from scratch, I would go with the wider wheelbase, because that would mean I could take my turns faster, or if I have a drunken conductor, the train's not going to flip over if he takes the turn too quick. But unfortunately, you're stuck with the fact that if you want this train to work on every railroad there is, you have to go with the standard. So we understand that. Tom talked about it in his previous talk, right? IP standards. IP standards are very important to make sure that things intercommunicate in a seamless way. And in the same way, we try to apply that to our technology. So I talked about our leading edge technology, which was, for example, our N7, but then we create derivatives. For example, N6 is a derivative of N7. And what we do is we introduced EUV technology to make it easier for people to get advantages, but minimizing the barrier to adoption. So the design rules are completely compatible. The SPICE models are pretty much identical. So you can take existing IP and just port it from N7 to N6. This is just a picture of one of the key steps in the process where we replaced 5 immersion masks with 1 EUV mask. So that's the power of EUV. And you can see the fidelity on the right is actually even better than what we had on the left. We give customers choices. And so, for example, with our N7, N6, we gave people the choice. You can either take your tape out and just go with EUV. You'll get a better defect density and lower process complexity. Or you can go with the bottom case where we offer an optimized process where you could keep your IP for your SRAM and your analog mixed signal, but you can redo a place and route for your logic and get a die shrink. So 2 different options. Again, just trying to make it easy as a standard. What that meant is all of our N7 and 6 IP was available very quickly because of that portability. It's a similar story when we look at N5, N4. When we first introduced N5, we introduced a device kicker a year later. Then we introduced a shrink, which is now a design rule compatible shrink. And then we introduced a further performance kicker with N4P, as well as an ultimate kicker with N5 and 4X. So again, the same concept of giving people an early technology, proving the technology, and then giving some derivatives which are more cost efficient, but allowing people to migrate very easily. And again, the same thing, because of that, the N4 IP is available very quickly because of the compatibility with N5. If you look at the D0s, what we found in N7 and N6 was the defect density was identical between N7 and N6. And the goal for N5 and N4 is the same. Actually, based on the results that I've seen, the defect density is identical already between N5 and N4. So what we do in terms of matching that process, but simplifying and optimizing, really does work. You will notice here that the N7, N6 curve, which is the green curve, is actually higher than the N5, N4. That's because that's the power of EUV. Because it allows us to simplify the process, it actually helps us to reduce the process defect density. Okay, so this is just a schematic of those derivatives showing you in terms of area. As you go from N7, N6, or N5 to N4, you'll get an area benefit, you'll get an energy benefit, and you'll get a speed benefit. So very easy migration with all those benefits. Okay, so this is a picture of a dog chasing its tail. And your first reaction might be, well, this stupid dog, he doesn't know what he's doing. Or you could say, hey, a smart dog, he's got a toy that's cheap, always available, and it's there. But I'm using it to introduce the picture of this. This is a train that is chasing its own tail. This is the second example of how you get a train up a steep slope. Not only the Americans had to do the transcontinental railroads, the Canadians had to do it as well. And this is a picture of the famous spiral tunnels in Canada. The locomotive you see on the top is actually maybe 50 feet higher than the train you see at the bottom, but it's the same train. It spirals on itself as it's going through a tunnel so that it can keep the slope under control as it's going over the Canadian Rockies. If a train can wrap around itself, there's no reason why a gate can. So that's the future, right? Nanosheets. And that's something we'll have in N2 nanometers. We'll have nanosheets will be the next step after FinFETs. They will give you even better electrostatic gate control, steeper subthreshold slope, and better channel conduction at low voltage. All of this takes a lot of money. TSMC is very committed to advanced technology. You can see here we're spending more than $4 billion a year on R&D, and we have about 8,000 people working on these processes as we go along. So when the railroad came in the West, towns literally sprang up where the railroad was. Because before there was nothing, but being by a railroad provided tremendous advantages in terms of transportation and such. And we kind of see Moore's law as the same thing. We open new territories by driving our logic to ever smaller dimensions. But then we use that knowledge to provide a whole bunch of other more specialty technologies. So you can see there, CIS going to 0.6 microns, RF and analog to kind of communicate with the outside world, high voltage, for example, to drive screens, and PMIC to power all of these devices. Some of the advanced cell phones today have over 30 PMIC chips, 30 little chips that are just figuring out how to send power to all of the other various chips across the system. So this is just another pictorial of this, where you can see all of these different more technologies are really the connection between the core logic and the real world that we experience. And we actually put it together in a very formal way. You can think about this as different wagons on a train, right? Everyone has a special use for carrying different types of merchandise. That's the same thing with these specialty technologies. We optimize them for a special use, versus our advanced technology is really about low power, low energy compute. So putting it together, for example, if you think of an IoT device, you're going to need logic technology, you're going to need RF and analog to communicate to the outside world, you're going to need ULL, ULP type of very low power technology because you're on a battery, you're going to need a PIMIC to connect with that battery, you're going to need some NVM to have the microcode. Everything kind of fits together, and high-V for a screen to create an IoT device. So we try to make these technologies come together so you folks can create some low-power, very long-lasting IoT devices. Specialty solutions require specialty innovations. This is my third example of bringing up a train up a steep track. This is actually the steepest train track in the world, 48%, which works out to about 25 degrees. And it required actually a new kind of innovation because the traditional cog railway looks like the picture on the left. Basically, you supplement the two traditional rails with a rail with some gears in it, and then you have a wheel with gears in it that latches on and brings your train up a steep slope. Seems like a pretty good solution, works for a lot of trains across the world, but not for 48%. So what this Swiss engineer came up with was he modified the design and he put the two gears side by side. So now, no matter how steep you go, this thing, the gears can't like pop out of the rails. They're kind of locked in, and you can go up this steep slope. And what this enabled in this particular instant was to make that travel 2 times shorter, made it economically viable. And they actually went out and got some bonds from the public to finance the project. And this thing has been going operational for, I think, around 150 years. So, example of an early startup in Switzerland with an innovation. So those types of steep slopes are what we're bringing to the specialty technologies. For example, in terms of IOF, very steep reductions in IOF so that you can maintain your battery life on IoT devices. Similarly, on the VDD, we drive very low voltages. So again, some of that enabled by FinFET with a steeper subthreshold slope. So you have very low active power and you can compute very efficiently. And then on the RF side, we typically think of RF as this technology which is big transistors, big devices. But in this case, for one, more and more of RF is moving to the digital domain, right? Anytime you can digitize something, it's going to be lower power. So it's changing the architectures. But we also have been able to optimize the FinFET for better FT and Fmax, and thereby lowering the power you need to transmit or receive in an RF applications. And basically what that means is I could download twice as much stuff on my phone with the same battery. Automotive, we take all of this. Autos are becoming computers on wheels. More and more chips going into auto. You've been a lot in the news in the last year with chip shortages. It brings tremendous advantages. The supply chain has been strained. We've actually been working very hard to kind of resolve some of that. But it's an area of incredible innovation. And what we do in auto is 4 major things, right? On technology, we optimize the technology for lower DPPM and make sure that the process qualification and the SPICE is more conservative. On manufacturing, on the IP ecosystem, and the reliability. So a lot of work goes into creating products that will make sure that as you drive your car, you can count on the fact that those electronics are going to work. Okay, I talked about how little towns sprang up on the railroad. The picture you see here, that red marker there is Port Townsend. It's at the head of Puget Sound. And it's a very similar location to San Francisco. And yet it's not world famous. And the only reason is it was vying to get the railroad, but guess which town got the railroad? Seattle. So in a similar way, we have a lot of nodes in our pocket Some nodes become major towns, major cities like Seattle. For example, 16 nanometers and 12 nanometers. I want to first of all bring your attention to the number of customer tapeouts. Ba, ba, ba. Isn't that a magic number? So actually, when I asked for an update 2 weeks ago about the number of tapeouts we had on 1612. And the number came back, ba, ba, chi. And I said, okay, I got 2 weeks. I'm sure there's another one coming. And yes, we did charge that customer more for that tape out because that's going to be a very successful product. But you can see very successful technology and very strong growth with that node. And that node has a very similar story to our N5, N4. Not only have we done a series of optimizations in terms of shrinks, layer reductions, device optimizations, and then coming back with further device optimizations, SRAM optimizations, smaller standard cells. So there's a whole history there of keeping to optimize that node. At the same time, we've added all the more than more technologies on it. So for example, the RF, on which we're seeing a lot of work, millimeter wave RF, auto is there, MRAM and RRAM, like Thomas talked about before. So a very successful node that's building a lot of infrastructure, both in the traditional logic and the more than more. One train is good, multiple trains are always better. And that's what we do with 3D fabric and packaging. We basically take multiple chips and put them together in a package and create some systems which are very, very powerful. You can see on the left there, we've got our 2D, 2.5D, which is INFO and CoWoS. Those have been in mass production for almost a decade. And they've enabled incredible things like CoWoS is basically what enables all the AI learning in the data center, the TPU chips. They use the HBM that Tom was talking about, as well as the logic. Up on the upper left there, upper right, you'll see we have our 3D IC, which is a pure 3D technology. Some of that is in early production, and it does enable exactly, again, what Tom was talking about SRAM being separate from the logic. For example, you can bring your level 4 cache on a separate die close to your logic, and that enables you, again, to minimize the distance and the energy you need to go to memory and create faster, more efficient systems. If I dive down just a little bit of detail into CoWoS, you'll notice on the left-hand side we have our CoWoS-S. That's the one that's been in production for 10 years, allowing the classical implementation you see here with the HBM and the SoC. On the right are some of the new offerings we have to further optimize this with CoWoS-R and CoWoS-L by creating silicon bridges and organic substrates to either reduce the cost, enhance the RC performance, or do the best of both worlds with CoWoS-L. Now, I would argue it takes a world to make Moore's Law happen. And there's a lot of people, we need to acknowledge in this journey. I think, together we can move mountains. And, we've really been able to accomplish tremendous things when you look at it. So the first people I want to recognize is our suppliers, right, for consumables. For example, could be wafers, mask blanks, or tool suppliers, a lot of whom are represented in the Valley here today. Some of them are in Netherlands, as you know, the EUV example I talked about. Some are in Japan. But we really depend on the help of those engineers to create all of that technology that we deliver. The second part is our partners. So from our IP ecosystem partners, so these are people that provide ready-made IPs that are proven so that our customers can really focus on their differentiating attribute, and they don't need to worry about creating this standard IP which is available off the shelf. The EDA vendors, again, very strong presence in the Valley. And the cloud providers, which is a mixture of EDA vendors and the cloud system companies. It used to be when you wanted to create a startup, you needed three things. You needed people, you needed computers, and you needed EDA licenses. The last two you can get on the cloud now. So all you need is people. It's not an easy problem, but makes it easier. And then finally, our DCA and VCA. So these are the people who help our customers by either providing design services or even full turnkey like an ASIC model. And then lastly, our customers, which basically take our technologies and literally create products that change the world. And think about the world we live in today, in 2022, and where we were in 2000. Would we have been able to survive a pandemic in 2000 with all this remote work and work from home? I don't think so. So tremendous work by everyone. And I think, there's never been a better time to be an engineer. This is, tremendous innovation happening. So, are we there yet? This is the Gold Spike Junction. This was the end of the Transcontinental Railroad. It was finished in 1869 at Promontory Point, Utah. But luckily, Moore's Law is still going. The obstacles are getting tougher, right? We have to cross steeper canyons. So we build more elaborate structures. And if we can't go over an obstacle, then we can always go under it. And the speed of innovation is changing. This is a prototype of a 600 kilometers per hour maglev train. That's how fast innovation is going these days. So with that, I want to summarize. My first key message is never underestimate human ingenuity. Never, ever, right? Whether it's for trains or Moore's Law, so many times we thought we hit a wall. Yes, we're hitting a bunch of walls, but we're figuring out different ways to create innovation, and we're changing our architectures to go around it. We're changing our process architectures, we're changing our design architectures, we're changing the products we're doing. On the TSMC side, we're powering the digital revolution. We have N3E in design right now with many customers, N2's on the roadmap with nanosheets. We have specialty solutions which complete the whole gamut with CIS, RF, NVM, and PIMX. We're putting more chips together with 3D packaging to enable entire systems. And it's really taking a whole world to complete this ecosystem. So I want to leave you with a final slide of enjoy the ride. Like I said, it's a time of innovation. When the Transcontinental Railroad was done, in the words of Wikipedia, what it did is provided safer, cheaper, faster travel to the West. Moore's Law is doing the same thing. We're providing cheaper, faster, more efficient technologies for your innovations. And together, we're really democratizing innovation. So, thank you very much for your attention. I'm happy to take...
present an appreciation token, a plaque to our speaker, Dr. Paul Rousseau.
Okay. He's wondering what the plaque is. Okay. Thank you.
Now we're open to questions. Our volunteer will hand the microphone to you.
Sure, thanks. Any questions? If it's not about Moore's Law, you can ask questions about trains as well. So let me answer one question from the previous session, if there's no questions yet. You had a question about what limits SRAM scaling. Pretty much, SRAM has been a structure that's been optimized for many, many generations. Whereas on the standard cells, there's a lot of things we can still do in terms of trying to optimize it. The SRAM has pretty much been optimized to death. And so its scaling is pretty much limited by fin pitch scaling as well as contacted poly pitch. And if you multiply those two together, you can pretty much predict what the SRAM size of a particular technology is going to be. So that's why you do see, I think I would say up to 7, we did not see much of a slowdown. But starting from 7, we are definitely seeing SRAM scaling slowing down because those two characteristics are very hard to scale.
Really interesting talk.
You need more than more technology to work there.
Yeah, that's right. So, great talk. I had one question in particular about the supply voltage. And what is the lower limit of that? Because there are a lot of applications that are using energy harvesting from really weak sources
Right.
of RF energy harvesting. And so that becomes important, the supply voltage.
Right. That's a great question. I think it depends a little bit on how much risk you're willing to take. And we have kind of various recommendations, but I would say somewhere around 0.35 to 0.4 volts. And it also depends on the VT you're using. Obviously, the higher VT is going to stop earlier. But we have some customers who have gone down to 0.35. Now, I think with nanosheets, we may be able to push that a little bit more. But the numbers I'm giving you right now are for FinFETs. So obviously, there's a lot of trade-offs with that. And the more logic you put in a particular stage, for example, the more risk you have of having one device that's just too slow. It's also a statistical problem. So sometimes it depends exactly on what you're trying to accomplish. But for simple logic, yeah, we think we can get down to about 0.35 volts.
Hello, Paul.
Hi.
I'm William, by the way.
Oh, okay.
Congratulations. I didn't think that you were going to be able to go through 80, 90 slides, but you did.
Okay.
and actually ahead of schedule.
I had to say, I didn't even look at the time.
I have a two-part question. The first one is related to current silicon technology. What do you envision maybe the next challenge beyond EUV? The second question is actually a follow-up of moving beyond silicon. What do you think that would be the next, after silicon, what would be next? Would be, the next 3 to 5 molecular type of thing?
Yes, yeah. Gallium arsenide has always been the technology of the future, right? No, I'm kidding. No, that's a tough one. That's a trick question because I think for years people have been predicting the demise of silicon. And I think, so let me go with the first question first. In terms of EUV, I think there is, as you know, there's a high aperture EUV on the roadmap. That has some pros and cons, but that's definitely probably the more likely thing that's coming, right? So definitely, ASML has that on their roadmap, and it's something we're looking at, but it's definitely, again, it's the cost doesn't get any easier and the technology doesn't get any easier. So there's definitely some trade-offs with that, but that's potentially another next step on the lithography side. In terms of what's next, I think maybe the best thing is for me to give you a teaser, right? So we will have our symposium mid-June, and our senior VP of R&D, Dr. YJ Mi, will talk about what we're doing in our research side. There's a lot of things going on. For now, I think the next big step is still we still have to climb the mountain of nanosheets. Right, so that's a challenge. It hasn't been in volume manufacturing yet, but there's a lot of new materials that we're looking at, and I don't know that I'm going to be brave enough to make a prediction, William. So.
Hello, Dr. Paul. Thank you very much for such a fascinating talk. This is Raymond from CIE side. I have a question. You showed a slide regarding to all the supplies to TSMC, right? And one particular area you mentioned is EDA.
Right.
I come from EDA background. I want to know, from current tools, what are the things that still needed, in innovation in EDA sector that you think will further propel your technology, helping TSMC to achieve more?
So I think that's a good question. We work very closely with the EDA vendors, and every generation we bring in new features to the technology that need to be implemented in the EDA tools. So for example, we'll talk about our FinFlex technology in the symposium. That's something that needed very close interaction with the EDA vendors to create that design enablement. One of the next big frontiers there is AI, right? Is how do we, because you've seen the numbers out there, right? These technologies are not getting any easier. And so the amount of money that you need and design work to, people quote, your first N5 tape out could cost you over $100 million. So the things that are happening in AI is probably the most exciting area of how we can reduce the design cost by optimizing some of the EDA flows. And that applies into many different areas. There's actually, Bill Daley from NVIDIA had an interesting talk at GTC on what they're doing on their side. And I hope you folks on the EDA vendors are doing a lot of good work there as well. We're really looking forward to it.
No more questions. Let's thank our speaker again.
Okay, thank you. Thank you.